name it at short transmission line, the second one is medium transmission line, and the third one is long transmission line. We are going to model each of these transmission lines. Firstly, we'll talk about the short transmission lines. Actually, the transmission lines, we can model the transmission line if its length is less than, if the length of its length is less than 200 kilometer, then we can model it. It means that we can ignore the distribution effect up to 200 kilometers. Up to 200 kilometers, it means that uh, after crossing 200 kilometers, we cannot lump the capacitance, inductance, or resistance. We can lump means collecting, adding together and making a model, making a circuit, a simple circuit, and then solve it. We can do this up to 200 kilometer. After 200 kilometer, we cannot make such a type of model. And more, if our transmission lines have distance more than 200 kilometer, then we call it a long transmission line. So we do modeling of short transmission lines and medium transmission lines, but in case of long transmission lines, we go for distributed network. So in short and medium transmission lines, we can lump the total resistance and reactance. So actually the transmission lines is divided into three types. Short transmission line less than 80 kilometer, medium transmission line is less than 200 kilometer. It means that if the line is more than 80 kilometer, we will consider it medium transmission lines. And if the line length is greater than 200 kilometer, we consider it long transmission line. So firstly, today we will talk about short plus medium, but firstly we are going to talk about short transmission lines. So there is one more thing. So if frequency is 50 hertz, length is 80 kilometer, if we multiply both of these, then the 400 kilometer per second is actually the speed of flow. You can call it, in case of, if greater than this 4000 kilometer per second, we can call it, it's actually the velocity. We can call it like the uh, actually we can call it short transmission line if less than this value, because in some countries 60 hertz. So if we will multiply 60 hertz with the length, with any length, if it is greater than 400 kilometers per second, we consider it short transmission line, and more than this we consider it medium transmission line. So in case of 50, we actually, if we divide 80 if we multiply 80 kilometer with 50 hertz, I will get 4000 kilometer per second. So if it's 60 hertz, maybe it is a bit different. Okay, so that's why I am talking, when I talk about the 80 kilometer and 80 kilometer or 200 kilometer, I am talking about the frequency of 50 hertz. So in case of 50 hertz, the short transmission line, if its length is more than 80 kilometer, we categorize it as short transmission line. As short transmission line has less capacitive factor, capacitive reactance, capacitive effect is less. So you know that the capacitive effect means capacitance is less, but the reactance is more, because I have told you that before in previous lecture, that the reactance in case of capacitance will be equal to 1 divided by 2 pi fc. Okay, so if capacitance is less, then its reactance will be more, capacitive reactance. So I'm talking about the, if I'm talking about the short transmission lines. In short transmission lines, we ignore the capacitive effect because its value is too less. We ignore it, capacitive effect. And of course, if the value of capacitance is too less, then the value of the capacitive reactance will be more. So normally what happened, I am telling you here, at sending end, we have, for example, here the current at sending end is, here is sending end voltage. The current at sending end is in short transmission lines, the current at sending end is equal to current at receiving end, because the capacitive capacitance in equivalent circuits, we always in transmission lines, we always connect capacitor in models in parallel. So if I'm connecting capacitance in parallel, then Is will not be equal to IR. So then there will be some current flow in ground through a capacitor of our circuit, of our model, as we ignore the capacitance over here. So we can say that sending end is equal to receiving end. This is the important point of short transmission lines. So so it has having less, so you ignore the capacitive effect. Okay, I explained it. So sending end current will be equal to receiving end current, as I explained now. So here is the model of here is the equivalent circuit of short transmission lines, as there is no parallel factor. So you know the current in series is equal. If we recall from the linear circuit analysis, the current is equal to the if there is no parallel component, then the current is current in series circuits, the current at entering point is equal to current at leaving point. So the here is the current enters is, we call it sending end current. This is generation side, and this is load side. We call it receiving end current. So in short transmission lines, receiving end current is equal to sending end current, because there is no capacitive effect here. So when we make a model about transmission lines, okay, this is constant. Okay, transmission lines, this in what's in is in the box is constant. Okay, because it's we can say that this transmission line is actually, it has some capacitance, some resistance, some inductance, uh, but the sending end and sending end current can be changed at any time. So we model like it model like we model like that input values, the input values in our system, maybe whether it is medium transmission lines, long or short transmission lines, the input to our system, to our transmission line, is sending end current and receiving end sending end voltage, and output is receiving end current and receiving end voltage. So these four things we consider it at as variables, because sometimes sending end current can be different from receiving sending end voltage uh, is different. If it's different, then the receiving end voltage will also be different. If sending end current is different, then the receiving end current can also be different. So but the other components are resistor, reactance, and capacitance. They depends upon length, so they will be constant. So I am just making a model that it's a model. It's a two-port model having two port. One is input port, one is output port. The input I will consider sending and two variables, sending end variables and receiving end variable. So I'm going to make a model of short transmission lines. Why I am going to make a model? Because it will help me in uh, actually it will help me in solving the problems, and it will help me in designing any kind of transmission line. So we will discuss about models. Okay, so here Vs is equal to A into Vr plus B into Ir, and Is is equal to C into Vr plus D into Vr. So this is the equation of this model. Okay, but how the equation of this model is like this, I am explaining to you now. So let's see. This is the equivalent circuit of our short transmission lines. I have already explained. So if we apply KVL over here, we will get Vs is equal to, because I think you know the KVL. So the KVL is the sum of all the voltages in a loop is equal to 0. Okay, so here we know that the this is voltage rise. Okay, because this is sending end voltage, and this is voltage drop, and this is also voltage drop, because this is transmission line, it drops the voltage. This is load, it also drops the voltage. We have two drops over here and one rise. So voltage rise is equal to voltage drop. This is KVL. Voltage rise is Vs, and voltage drop is Vr plus the drop across these two components. So I know that by Ohm's law, I can find the drop across this component. V is equal to IR. So I write IR, and I can also find the drop across this component. V is equal to IX. So I write IX. Because there is no capacitance, so I named it as XL, the inductive reactance. So And I told you before that it is the reactance is actually the imaginary component. If we write impedance, we always write like this R plus, this is imaginary component, R plus jx. So actually the impedance is a complex number. It means that it has imaginary part as well as it has real part. It has two parts. So we always write reactance in imaginary side. So that's why we write it here, XL. So it is IXL drop, or you can also write like this. I can write Z, which is easy for me. This is the Z multiplied by I is a drop across the transmission line, and VR is the drop across the load, or we can say that this is the voltage applied to load. So I have written here. Okay, so we apply KVL over here, and then Vs is equal to VR plus Iz. I just change R plus JXL is impedance is equal to impedance. I replace the value over here with impedance. We denote it by Z. So as we know that Is is equal to IR, I have explained because it's series circuit. So sending end current is equal to receiving end current. I have explained it before. By comparing the two-port model with the equivalent circuit equations we get. Now, this is the two-port model, okay? Now we can compare these, and I will see that the R plus JXL, okay, this is the value, okay? Vs and Is, if I compare these two values, these two equations, these four equations, I will get here, I will compare VR with VR, okay? So I will get A is equal to 1, B is equal to Z, and C is equal to 0, and D is equal to 1. I'm going to get this. So these are the constants of our model, A, B, C, D. There are four constants, A, B, C, D, even in medium transmission lines and in short transmission lines. If we know the constant, we can find the other values. So these are important. So in medium transmission lines, in short transmission lines, you always have these constants. So if someone asks you to find the constants A, B, C, D of short transmission line, so you already have two constants. Okay, so the value of, if I have 5 ohm resistance over here, and for example, if I have 10 10 ohm reactance over here, J10. So I will just write B is equal to 5 plus J10. So these are the constants. So if I have this constant, any constants, I can find the sending end voltage. Okay. For example, I have receiving end current and receiving end voltage. I can just multiply A is 1. Okay. I will just put the value of these constants here. I'm going to get the values of these voltage and this current. Or if I have sending end voltage and sending end current, I can get receiving end voltage and receiving end current by putting the values of constants. For every short transmission lines, we have the value of constant is same. A is equal to 1, B is equal to Z, C is equal to 0, D is equal to 1. Okay, these are the constant of short transmission line. So don't get confused over here. Even in medium transmission lines, we are going to use these constants. So for short transmission lines, the value of constants are different. For medium transmission lines, the value of constants are different. And in medium transmission lines, we use two types of models. In short transmission line, we use just one model. Okay, this model is this circuit. But in medium transmission lines, we are going to use two models. So for two models, the value of constants are different over there too. So here, so if someone tell you it's short transmission lines, you must know A is equal to 1, B is equal to Z, C is equal to 0, D is equal to 1. Okay, that's all. After that, you are going to put the values in this equation and you will get, we will solve problem at the end of medium transmission lines. But here, I am just telling you that how you can find the uh, values of these constants, and then after putting these constant over here, you can find the value of these variables. Actually there are four variables, 1 2 3 4. So if someone give, if in question normally two variables are given and you have to find other two. So it's easy, two equations, two variables, no problem for us. So let's move towards the making model of short transmission lines. As I have told you, actually we already, uh, so in matrix form we can write like this, okay? A, B, C, D. If someone asks you to find the matrix of constants, you can just write like A, B, C, D. It's nothing complex over here. We just, what we did, we have written these equations in the form of matrix over here. So I will just put the value of A is equal to 1, B is equal to Z, 1, Z, 0, 1. And we can also find these values by using matrix method, and we can also find these values by using linear method, linear equation, by solving linear equations by substitution method. Okay, at no load, you know that here, let me explain something which we call it charging current. Actually, charging, what is charging current? Okay, so we must know, because in problem someone somewhere is
Hello.
it is in problems you will see the this terminology, the charging current. So for example, if I have, in the last slide, okay, I'm repeating this, okay, on the last slide I'm repeating this. Okay, actually I just converted this the equation of this model in matrix form, nothing else, and then I can also solve this problem, these transmission lines related problems in the terms of matrices. So at no load, current is zero. Okay, so one thing here, you must know that what is charging current here. The charging current, that you know, the at no load current is zero. So in medium transmission lines, even there is, for example, this is medium transmission line. Okay, I'm not trying here the inductances model or something. I just drawing two components. This is, okay, this is standing end current. Okay, normally in open circuit current is zero, but in medium transmission line there is parallel component, so we cannot say that the current is zero, even if no load at transmission line. For example, in case the transmission line has no load, here load is not connected, so transmission line will be open from receiving side because load is not connected. So the current here will flow in capacitors, capacitor, capacitive component. The current will flow in capacitive component. So this current we call it charging current of transmission line. Even in no load there is current, we call it charging current. But what happened in so if someone asks you what is charging current of transmission line, you can just reply that in no load conditions, normally in normal circuit and LCI, we have learned that in no load there will be no current in our circuit. Okay, but in no load here is current. That current is due to the capacitive effect of transmission line. There is some current that flows from transmission lines to ground through capacitor. Okay, so but in short transmission line there is no line charging current. So in no load current, we can all, as among all constants, C is, that's why C is zero. So in medium transmission lines you will see that there is C is not zero. Actually C is zero because of, because sending end current is equal to receiving end current. If sending end current is not equal to receiving end current, then C will have some value. So as short transmission lines have no charging current, no line charging current, so that's why we have value of C is zero. So for example, someone will ask you that why the value of C is zero. You can reply like this: find Vs through phasor diagram. Okay, so here is the phasor diagram we are going to discuss a bit. So actually, if load is lagging, normally the on system load is lagging. Okay, if load is lagging, the voltage leads the current or current is lagging. So if load is lagging, we can say that, okay, don't look at this diagram. We can just like write here. I can okay, if load is lagging, then voltage leads the current. We know that in power system, if load is lagging, then the voltage will make some angle with current. You know the lagging load. Lagging load means inductive loads. Okay, the short transmission lines don't have any capacitors. So if even in open circuit, it will act as lagging. So lagging means the inductive load, the inductor load. If there is load in the system is inductor, then the voltage and angle with voltage and current will make some angle. So if even if in capacitor, if the load is capacitor, they will also some make angle. But in inductive load, the voltage is ahead than current. It means that the voltage will make some angle with current. We call it as receiving angle, okay, theta r, because this is receiving at voltage Vr. So receiving end voltage and receiving end current, because we are talking about the load, so load is connected on receiving end, it will make some angle. We call it theta r. So how I am going to find the Vs in as a phasor in phasor, okay? So here, so this is the Vr. So this is the equation Vs is equal to Vr plus IR R plus IR XL. This is just from KVL from the last PPT. So last slide. So IR, as you know that the resistive component, in resistive component, current and voltage are in same phase. So current is at 0 degree, okay? So I'm just drawing it like this. I'm adding this component. Firstly, I add this one, then this is the vector adding. Then I will resistor and reactance, okay? Resistance and reactance. Resistance and reactance always make 90 degree to each other angle. We must know it, okay? If it is, you know that if it is resistance, it is reactance. Here we are going to get impedance. That's why we call that impedance is equal to R plus Jx. This happens in case of inductors. But in the case of capacitor, if the load is capacitive, then I will tell you what happened. So actually you know that the component resistor always, the component of resistor is always as 0 degree. Okay, so I will just put it like this, IR into R, because R angle is 0. So with respect to reactance, so if I will add reactance, I must add it at 90 degree, and this is a scalar addition and vector addition, and I'm going to get the total value Vs here, the sending end voltage, and the angle which it will made will be the sending end angle. Okay, so this diagram is actually a phasor diagram. If someone tell you that explain the phasor diagram of transmission line, you can just explain it like this. So why I have calculated like this, because I have calculated like this. Now I can explain further about the equation of sending end voltage. Okay. So there are actually 3 points on this phasor diagram I have explained here. Just above this, I just drawn this now, and then now I am drawing the points. This is 0 point. This is A. This is B. This is C. Okay. So from this triangle, if I will look about this is the hypotenuse, this is the perpendicular, OB is base. So hypotenuse square is equal to base square plus perpendicular, because this is, you know, this phasor gave me the angle of sending end voltage. Now I want to get the angle, because it is important in power system design. We must know the angle of sending end voltage with the receiving end current, or with the receiving end voltage. We must know the angle. So actually, I am just explaining that you must clear about the phasor diagrams, because in future you are also going to use it in power system analysis too. So these are 4 points on the triangle. I have found the angle from here. This is the sending end angle. Now I will see the what is the magnitude of this sending end voltage, how I can find through phasor diagram. Okay, so OC square is equal to OB square plus BC square. This is the hypotenuse square is equal to base square plus perpendicular square. So OC is actually the sending end voltage, you know, VS. I just put the value over here. OB is OB square. OB is actually the, this is the X component of VR. So you know that the X component of VR is cos theta and Y component is sin theta of any vector. So we write here VR cos theta plus IR into IR multiplied by R. It is the same, okay, over here or here. The distance from A point to B point is IR into R. So I just written, instead of OB square, I written that VR cos theta. The component of VR x is here. So VR x is equal to VR cos theta. So O to A plus A to B. So O to A is VR cos theta and A to B is IR into R square. Now I will put the value of BC. BC, you know that this is the from this point to point B, the distance is equal to from this point to point A. So I can write as VR sine theta and the angle is R, receiving end voltage angle. So plus this value IR into X. As I am talking about the magnitudes, I am not going to in complex number or anything. So we can just take the magnitude of this one and then the magnitude of this one. Sorry, we will just multiply this, sorry, not magnitude. We'll just solve it and then we will find the value of Vs we can find from here. Vs square is equal to, actually there is no square because I took the under root from both sides. So it is just, actually it is just, I explained that how you can find the value of Vs from the phasor through phasor diagram. But in your problems, phasor is not given. They just talk about the constants. So that's why I just explained a bit here, nothing else. You don't need to worry about this phasor if you just want to solve the problems provided by your professor. So voltage regulation, the voltage regulation is actually the VR at no load minus VR at full load divided by VR full load. Actually, I got the signal problems. I am repeating again. Okay, I'm repeating again. Okay, sorry, I have signal problems. So voltage regulation, actually, in the last two PPTs, it's just a phasor. I just explained that how you can find the angle of sending end voltage, because the angle of this is AC power. Okay, we will talk about angles and magnitudes. So that's why I explained the phasor diagram here. The angle you can find from by adding vectors, you can find from here, and you can also find the magnitude of Vs. Is it just the base magnitude square plus hypotenuse plus perpendicular magnitude square? So nothing else. I just explained over here. Did you get my point? Do you want to ask some questions? You can ask now. Okay, we just move towards the voltage regulation. So actually the voltage regulation is the voltage we are receiving at voltage at no load minus receiving at voltage. This is also in same, okay, we are not, it's not big R. So this is a sending end voltage at no load minus sending end voltage full load divided by full load. This is the voltage regulation formula, that how your voltage can regulate. It's just a formula, nothing else. So if someone asks you to find the voltage regulation of transmission line, you just put the value of VR at no load minus VR at full load. Full load will be given in the question. That the value of full load, we will find the voltage at full load and we will find the voltage at no load. We will subtract both the values and divide by full load. We know that the full load voltage will be less. So for example, at no load, my voltage is, for example, is 100 volt. At full load, the voltage is, for example, it's 90 volt. 100 minus 90 divided by 90. So actually, it's just tell the percentage of voltage regulation, nothing else. So it's a formula, you have to remember this. So until now, you have to remember, up to now, you have to remember the constants, of medium transmission line, and this formula voltage regulation, and the formula of that model. You must know this. Okay, this formula is important. This you must know this, and you must know the what are the values of the constants in case of short transmission lines. So now we will move towards the okay, performance of transmission lines. The efficiency is actually the simple a formula, is nothing else. If you want to find the efficiency of power transmission lines, just put the power received at receiving end divided by power delivered at sending end. Okay, and power received at receiving end, power delivered at sending end plus losses. If you want to include the losses, you will add the sorry, it's a sending end. You have two methods you can find the efficiency. First one is, you know the sending end power, you know the receiving end power, you just divide and multiply by 100. Of course, the sending end power will be more because there are losses in transmission lines. But if you don't have the sending end power, you just have the receiving end power, and you know the receiving end current, you just can use this formula, that receiving end power at receiving end plus 3 I square R. I square R losses I have explained before, that what are I square R losses. So why we multiplied it with 3? Because there are three phase line. This is the efficiency of three phase line, so we multiplied by 3. In case of single phase line, we just remove the 3 from here, because there are three lines, so there are three receiving currents, so that's why I multiplied it by 3. So that all from short transmission lines. Now we move towards the long transmission line. Long transmission lines, in short transmission line, normally there are no in your sheets you don't have problems. If in case someone asks you to find the value of sending end voltage or receiving end voltage for short transmission line, you will just use this formula, and you know this constant, you can find it easily. We will solve one problem at the end of medium transmission lines, you will know there. So now I'm moving towards the medium transmission lines. If you have any questions in short transmission lines, you can ask. Otherwise, we move towards the medium transmission lines. If you have any question, you can type in WeChat in chat here over here. So okay, so we move towards the medium transmission lines. So in previous lecture, we have learned about the short transmission line. Now the medium transmission lines is having a distance more than 80 kilometer. These are categorized in 50 hertz system. They are categorized as medium transmission lines. So medium transmission lines actually have two types of models. This is the first one. We call it T model. Actually, we find the resistance of total resistance of transmission line. Then we find the total resistance of uh, the total reactance of transmission line, and then we find the admittance, because I had told you that why we are going to find the admittance in my previous lectures, because the medium transmission line have capacitive effect. In short transmission line, we don't have this component, so that's why we just combined that. But now we have this component, and we can model our transmission lines, and we can categorize our medium transmission lines in two models, whether it is T model or it is pi model. Why it is T? Why we call it T? Because its shape is like T. If you write T over here, you will know that its shape is like T. So that's why we call it T model. So here we will find the resistance of transmission line. If we know that resistance of transmission line, for example, it is 10 ohm, I will write 5 ohm over here and 5 ohm over here. For example, if I have 50 ohm reactance of transmission line, I will write 25 ohm here, 25 ohm here. So in case of admittance, it is lumped in the middle of both these resistances. We divide the resistance and then lumped it. We divide the resistance and reactance and then lumped the capacitance over here. Okay, we just show it at one point. So this is a T model. So in question, someone if in question it is given that you have to find the constant of T model, then you have to know we have different constants for each model. So you must firstly, when you see the numerical or a problem related to transmission lines, you must know that whether it is T model or pi model. You must have this knowledge before solving the questions, otherwise you will not solve right. Okay, distance more than 80 kilometer, I have told you, and less than 200 kilometer is medium transmission lines. So we are discussing about T model. We will again use the same two-port modeling here. This is the transmission line. These are the input variables. These are the output variables, and these A, B, C, D are four constants over here. So the formula will also remain the same. So you just have to remember one formula, and you are going to get the you can solve the all the problems. There is no different formulas. What is different? Difference is the constant is different here. A, B, C, D, A, B, C, and D will be the different for medium transmission lines. So we will solve, let's solve this for T model. So let's apply KVL, because the same thing which we did in our previous lecture, that we are going to find the values of constants here for our T model. So for that reason we have to solve our circuit. So you know that the receiving end voltage over here, we apply the KVL at the second loop. So we will get VAB. The EAB is the voltage from here to here, from this point to this point. The voltage is AB. So if we apply KVL level here, we know that the VAB is equal to VR plus Z divided by 2. Why I call it Z divided by 2, Z divided by 2? Because the total admittance of total impedance of line will be the R is equal to Z is equal to R plus R plus complex number is J X L. Okay, that's why the resistance is halved over here and halved over here. Reactance is halved over here. So that's why I just have written that Z divided by 2. So VAB is equal to, I am talking about the second loop. So I will applying KVL here. VAB is equal to VR plus I into impedance. You know that voltage is equal to, this formula, I think you know that V is equal to uh, V is equal to I into Z. It's same like V is equal to IR or V is equal to IX. These formulas are same. So here Z divided by 2. So I just have written Z divided by 2 into IR. I have just have written the voltage drop from this point to this point. So applying KVL, I got VAB, and then after that, now IAB. You know the IAB, I is equal to V divided by R. Okay, V divided by R. So here there is no R. We are talking about the AC circuits. We are talking about the impedance over here. Impedance is same like resistance. While you are solving circuit, you just consider the impedance same like a resistance. So I is equal to V divided by R in case of Ohm law. In case of AC circuits, I is equal to V divided by Z in case of AC circuits. So I have written over here, actually the here is wrong. I is equal to V divided by Z. In the last lecture, I told you the admittance, that admittance is inversely related with, you can say that inversely related with impedance or inversely related with reactance, same thing. I have told you this before. Why? This is admittance. So 1 over ZAB we have replaced with 1 over ZAB is equal to YAB, or we just call it Y over here, okay? Because there is only one parallel component here. So we just call it Y, don't call it YAB. It's the same thing. So 1 over ZAB is removed by YAB. Here is replaced by Y here. And this is not ZAB, this is VAB. This is not Z, this is V. Because ZAB we have replaced over here. Okay. So now you know that now I know the VAB value and IAB value. By now I apply the KCL over here, and I'm going to find the standing end current, because I have to know the value of standing end current here. So I will apply KCL over here. So IS sending end current is equal to IR plus IAB. So I have found the value of IAB, which is equal to admittance into uh, VAB. This is not ZAB. Okay, it is wrong over here. So I just put the value over here IR plus Y, and in I put I have written the value of IAB, which is equal to Y into ZAB. I just put the value. Okay, let me explain over here. This is VAB. Okay, so I put the value of VAB in this equation, and then I will get IAB, and then I put the value of IAB over here. Then I got this equation. You can solve later. It is not difficult. Okay, I am just going. I just move onwards. Okay, for by Kirchhoff's voltage, so I got the value of Is. Now I am going for value of Vs. So by Kirchhoff's voltage law, Vs is equal to, you know that applying KVL over here, Vs is equal to Vb plus Z divided by 2 into Is, the same over here. The difference is that here is sending end voltage and sending end current, and here is receiving end voltage and receiving end current. So I will just put the value of Is over here because I have value of Is. I will put over here, and by now I have this equation Vs, I have this equation Is. I will compare both of this equation after solving it. Okay, it is not solved well. So after I will compare these two equations. One is derived from circuit. I compared with this model, this two-port model. Then I got the constants like this. This is the value of A, B, C, and D. So in case of transmission, medium transmission line, the value of the constant value A and D is 1 plus Zy divided by 2. For constant value B is Z into 1 plus Zy divided by 4, and this is the constant C, and this is the constant D, which is the same. Constant A and D are same. Okay. So until now, if you have any questions, you can ask, or we move forward. Okay, so we move forward for pi model. So you can ask now. I have opened your mic.
I just want to check the last slide again.
This one.
Please. No, the one after it. After it. I guess this one. Just a second, please.
You are writing, right?
Yes.
Okay. Okay, so we move towards the pi model. In pi model, you know the why we call it pi model, because it's look like this, pi. So we call it pi model. That's all. So you know that the sending. So what we did here, we didn't distribute the resistance and reactance, but we distributed the capacitance. We lumped it on the sending end as well as receiving end capacitance. We lumped it on two sides. So it's we call it pi model. So there are two models. The first one is T, the second one is pi. So here I'm going to find the value of constants again. Okay, A, B, C, D. So VAB, we know that the VAB is VR. Why it is VR? Because uh, this capacitor is connected parallel to load. Okay, so the voltage provided to load is VR. So voltage in parallel is same. You know that the voltage in parallel is always same. If two components are connected in parallel, they have same voltage. So VR is equal to VAB. I have just written over here. So VAB is equal to VR. So ZAB is equal to 1 over YAB. As I have explained before, that impedance is inversely related with admittance. So admittance is YAB. So there is nothing special over here, nothing new over here. IAB is equal to VAB divided by ZAB. because I want to find the value of IR and IS. So that's why firstly I have to know the value of IAB. So what is I is equal to V divided by Z, V divided by R, V divided by Z. So what is value of VAB is VR. So I put the value of VR over here. And what is ZAB is 1 over YAB, or we just call it Y, okay? So y divided by 2, because there is only one y. We just divided it y over 2 over, we just divided it in two components, but there is only one y. So y divided by 2 into VR. I just put these values here. So by KCL at node A, now we apply KCL and find the value of IR, because I want to know the value of IR. But for that value, firstly, I have to know this value I. So I is equal to IR plus IAB. Okay, this is KCL at node A. The current entering is equal to sum of current entering is equal to sum of current leaving. The current enters over here is I. The current leaving from here is IAB and IR. So what I did, I just put this value IAB over here. So I'm going reversely by solving this circuit. Vs is equal to VCD. Now Vs is equal to VCD. The same thing over here. The voltage in parallel is same. So Vs will be equal to the VCD, and VCD will equal to the VAB plus ZI. This is KVL over here. If you apply KVL in middle loop, you will get VCD equal to VAB plus drop over here, Z into I. So this is just like this. Sending end voltage is equal to VAB plus ZI. So I can write VAB as you know that the VAB is equal to receiving end voltage. I just replace VAB with VR, and I just write the value of I, which I have found over here. I just put this value in this equation, and I got this equation. Vs is equal to 1 plus Zy divided by 2 into VR plus Zi. I got the first equation. Now I'm going for second equation. What is our second equation? The second equation is our this. I got this one, Vs is equal to AVR plus BIR. Now I'm going for this, Is is equal to. So second equation involves sending end current. So we know that ICD is equal to V divided by Z, is the same from Ohm's law. I is equal to V divided by Z, and I is equal to Y by 2 into Vs, is the same. I distributed the capacitors in two parts. So that's why admittance in two parts. I is equal to admittance divided by 2 into Vs. So I'm going to put the value of Vs over here. Okay, I already found here. So I'm going to get the value of Is, then Is is equal to I plus ICD. Is is equal to ICD plus I by KVL if you apply KCL at node C. So in this way, I got two equations, both of these equations, and I will compare both of these equations with the model, and I'm going to get the constants over here. So what are the constants over here? A and D are again same, 1 over 1 plus Zy divided by 2. In case of pi model, the constants, the value of B constant is Z, Z, and the value of C constant is Y into 1 plus Zy divided by 4. So you must know the value of all. So we drive the constants in case of short transmission lines, in case of medium transmission line, pi T model, in case of medium transmission line, pi model. So all these constants, after these constants, I am moving towards the problem. Okay. So until now, if you have any question, you can ask. So if you don't have, we move forward.
Oh, I have a question.
Do you have any question? Okay, you have opened your mic.
I just want to ask, is it easier to answer in the normal equations we got of the Vs and Is, or in this equation, like the Vs, Is, the one in front of me?
You are talking about the problems, right?
Yes.
So actually, it's not easy. It's not too easy. We have to use some techniques. I will show you in my next problem.
Okay, sure.
Okay. Normally, if you know the actually, if you will recall from the previous semesters, so it's easy. So this is the solved problem. We are going for it. A three-phase, this is the first problem on your sheet number 4, I think, or 5. So three-phase transmission line has the following parameters. We have three parameter: resistance, uh, inductance, and capacitance. Firstly, first, when you want to solve the problem, firstly you must know that which type of transmission line is this. So if the line is 150 kilometer, so we know that it is more than 80 kilometer and less than 200 kilometers. So we will categorize it as, we will consider it as medium transmission line. So what we have to find the voltage at the open end. Okay, open end means, you know, if the line is okay, I will just uh, read this question, this numerical, this problem. If the line is 150 kilometer long, find the equivalent circuit elements. It means, firstly you have to draw the equivalent circuit. This is pi model. Okay, we have to, this is pi model. Firstly we have to draw the equivalent circuit elements for using nominal pi model, not t model, pi model. If the line is open, firstly we will just solve the first part of question. Okay, then we will go if the line is open circuit. Okay, just we will solve from here to here. Okay, I will draw the circuit, I will find the, so for pi model, I must know the total resistance of the line, the total reactance of the line, then I can divide it like pi model. Okay, so firstly I must know the total resistance, total inductance, and total capacitance of the line. But problem is that here it is not given the total values. The parameter of transmission lines are per kilometer value. So we will just multiply it with distance in case of resistance and inductance. But in case of capacitance, I have told you that we cannot multiply it with distance directly. So firstly, I have multiplied this value with 150 kilometer. Kilometer was cancelled with kilometer, and 150 multiplied by 0.074. So it was 1.11 ohm. Okay, you can try it at home after the lecture. So inductance is 12.12 multiplied by 10 to the minus 4 Henry per kilometer. So I will just multiply it with 150 and I will get the total inductance of transmission line, okay, which is 0. Okay, I can repeat it again. Okay, I can repeat it again. Okay, wait. Okay, so I'm repeating it again. You know that we have to find the total resistance of transmission line. So this is the per kilometer resistance. Okay, so I have to find the total resistance first. After that, I can draw model. I can draw equivalent circuit. So this is the per